Okay then, so I want to at least sketch and hopefully fully prove this result here. So it's basically about how we can express a limit as a equalizer of a couple of arrows. Now, I suppose I ought to recap, I did say in the last video, but I'll recap what this R and S are. So I've got a better diagram somewhere. Maybe I don't. Well, probably here will do as good as anything. So if we have this upper triangle here, basically defines what R is. Okay, so we have this functor which goes from this category I to this category C, and it sort of it sends objects in I to objects in C. So we have these objects. I'm going to assume these I's are numbers, okay, in the index category. So we have A1, A2, A3, and so on, and they're going to be different objects in C. And they're sort of the images of the objects in I. Now, we're going to take the product of all of those. So we have this product object here, and then R is an arrow from that to this other product, and this is a product over the arrows of I of A of the target of I, the object at its target. And R is defined to be unique such that for any arrow F dash from J to K in I, we have that this triangle commutes. So what does that basically mean? Well, what it basically means is that we can think of a kind of generalized element of this product here, let's say a H element, as an assignment of a H element to every AI. If you're thinking of sets, you might want to think of H as the terminal object, and then you'd literally be talking about a tuple of one element from each of these sets AI, when C is a set. But anyway, more generally, it's just a tuple of H elements. And if we go along the diagram this way, we're basically just taking the kth such H elements out. So that would be the corresponding arrow from H to AK. And we want that to be the same as what we get when we take this sort of tuple of H elements and we apply R to it, so that'll give us a tuple of these elements. And this is going to be, there's going to be one such entry in the tuple for each arrow. Of the index category. And somehow R takes a kind of H element of AI and gives us a H element. Well, it takes all these elements and then it gives us these elements of the targets of the edges. And it's such that if we apply F dash on this particular one, then we get the same result. So essentially what it's saying is that like here's an assignment of a H element. Well, as imagine there's an assignment of a H element to every AI. Then we've sort of got our index, we've got our diagram, and we can imagine every sort of object in that diagram has something assigned to it. And then this is somehow a product over the objects, a product over the arrows in the diagram. And what this is saying is that every arrow is assigned the same object as its target is here. So when we have V, we assign objects to here, and when we do RV, we assign objects to the targets of the arrows in the corresponding way. Sort of simpler algebraically, really, is that well, we have it here. Maybe this is better. If we have a H element, V equals x1, x2, blah, 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 in this product of the AIs, and that's V, then RV is going to have a component for every, it's going to have a component for every arrow in the index category, and the component y of f of m associated with an arrow f of m is just going to be x of target f of m. So we just look at that original assignment of H elements and see how it assigns stuff to the target of each arrow. So I mean, in sets, this is pretty simple. If working in sets and H is equal to the terminal object, then such a tuple of x's like this is just going to be an assignment of one member. It's just going to be choosing one member from each of the AI sets. So it's just like a tuple. And then all this is it associates every arrow with the entry that got assigned to its target. So basically, if we imagine we have this set of elements, well, we have this tuple of elements, one from each, then this, and that's V, then RV is basically just giving us a tuple indexed by the arrows, where the entry indexed by arrow f of m is the element in the original tuple up here that arrow is pointing at. Okay, so that's the way we can kind of get a visual grasp on this. But I mean, the idea is basically similar, sort of generalized. Anyway, the other sort of mind-bending concept, I suppose, is this idea of S, which is a similar sort of beast. So S is again defined as an arrow from this product of AIs to this product over the arrows of A of target of the arrow. But now it's defined so that this square commutes for every arrow f dash from j to k. So what this means is, well, sort of related. So again, we can think about how this works on generalized elements. And basically, if we have an arrow v from h to this product, well, we can view this as a tuple of entries going into that product. Now, so that's a product over the objects in our diagram, and this is sort of selecting one h element for each of the objects in our diagram. Now, so that's what v is. Now, s of v is going to be selecting a tuple of h elements like this, one for each arrow. So for each arrow, we have a h elements of the object which is its target in the diagram. Okay. And how is this defined? Well, so if we call this tuple like this, yf1, yf2, blah, 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 then yfm is going to be SV, is going to be qf sv, like this. And according to this diagram, like doing q of fms is equivalent to doing af dash and pj. So what this is basically saying is that the way this tuple of arrows is defined is that y of f of m equals afm xj. So the way that we can understand this in the category of sets, it's often good to go back to the simple cases. So if we have a arrow v from the, well, say we're working as a c equals set just for now, and h is terminal object, then this tuple of x's again is just one member from each of these sets. And so we have this tuple, one from each of these sets. We have an x1 from a1 and x2 from a2 and so on. And then when we do s on v, we generate a new tuple in here. And so that's going to be a tuple of y's. And we want that y of f of m is equal to the arrow f of m lifted and operated on x of j. So basically, in this case, we take all these entries for our objects, and we know that this stuff's indexed by arrows. And so to work out a particular entry, we just take that arrow and find out what function it is, and sort of take the entry from this product that corresponds to its source and operate that lifted arrow a of f dash, that function, on the element of the source. So we're basically doing a of f dash on xj, and that'll give us the f dash element in this tuple here. So that'll give us y of f dash or fm, whatever you call it. But anyway, some arrow that goes from j to k. Right, so that's a quick reminder of the definitions of R and S. And so now we have this result that basically, I mean, I usually think when you're dealing with limits, if you can work out what the apex is, you're pretty much done. Normally the projections are pretty simple to understand. And anyway, well, they are in this case as well. But what we have is that this equalizer, capital L, with this monic arrow, little l, to this product, we're saying that this will be an equalizer of R and S if and only if L is the apex of a limit with natural transformation / cone phi, where phi is equal to pi after L. Okay, so how can we understand this intuitively? Well, intuitively, if you think about the category of sets, for example, it's kind of interesting actually. What is a limit in the category of sets? Well, it's the set of all tuples with one entry from each object, which have the property that if we do any of the lifted arrows on those entries, then the sort of output of the arrow, the corresponding entry, will be the output in the list. Will be the other sort of output in the list / tuple. Okay. So we see that basically it's what a limit. Well, so anyway, that's interesting because basically this result says that we can construct in general limits just like that. We take the product of all of the objects and then we select the ones which equalize these two things, which basically are doing those operations. I mean, when we have a generalized H element of this product, when we do R on it, we get the list of a list over the arrows of what the target of that arrow got assigned to, and so that's what R does. And when we do S on that tuple of X's, we get a list over the arrows of what happens when you sort of feed in the appropriate value of the source of that arrow and operate it as a lifted function. So we basically want to pick the entries of which this is the in such a way that these two things work out similar. So, I mean, if I call that property that R and S are equalized, that this arrow equalizes R and S, then I mean, we can see that a cone really is something that equalizes R and S in general. I mean, that's one of the things we get out of this proof. But the limiting cone has precisely the generalized elements which equalize R and S. It doesn't have any duplicates and it doesn't have anything missing. but in general, other cones might have other extra stuff, duplicates, etc. So we really start to understand what a limit is with this result, I think. Anyway, what's the claim? It's that capital L with this arrow little l into the product is an equalizer of R and S, if and only if this cone with apex L, which goes to A, with arrows phi, is a limit where phi I equals Pi after L. So, I mean, that's kind of just what you'd expect. I mean, that's just what a limit looks like in set. Anyway, let's get on with actually trying to prove it. So there's going to be two results which are going to come in especially handy for this proof. So here's one of them. So assume that we just have a general arrow T an arrow H from T to this product over the AIs. Okay. Well then, I claim this result, that we're going to have the RH equals SH if and only if we have the QF-RH is equal to QF-SH for every arrow F- of the index category, and that this is true if and only if psi k equals A of F- after psi j, where psi k is just pk after h. Okay, so it's just basically the projection. So this condition here, if we think of the size as components of a natural transformation from delta t to a, then this condition here ought to look a lot like the naturality condition, and indeed that's exactly what it is. So we're basically saying that H that equalizes R and S corresponds to a natural transformation. So if we go back up here, I mean, for any H to this product, we can just compose, we can just do H after P1 to get psi1, H after P2 to get psi2. We can extract these components and think of H as a list of these components. And we can do and we may have that R of H is equal to S of H. Now, what I'm saying is that when that's true, and in fact precisely when that's true, these psi's are going to look like a natural transformation from delta t to a. Okay, so what do we need to have a natural transformation from delta t to a? Well, we need a psi I from t to ai for every I, and they need to commute with the arrows in the sort of base of the cone. And that's precisely this condition. Okay, so this is what we want, but let's prove this result. So we have RH equals SH if and only if Q of F dash RH is Q of F dash SH for every F dash. Now this took me a while to get, but basically the reason that's true, I mean, obviously this implies this, but why does this imply this? Well, the reason is sort of component-wise reasoning, because whenever we have RH, that's a sort of T element of this product here over arrows, and therefore it can be written as a kind of ordered list over the sort of an element of a targ F1 followed by an element of a targ F2, I mean a T element of them, and so on. And the point is that two such arrows are going to be equal precisely when they're equal on those components. And you can see that because, if they're different on components, well, I mean, it basically all follows from the uniqueness of intermediary arrows in the product. I mean, if they're different on components, they're obviously different. Okay, if they're the same on components, that means if you do the PIs on the different components, you get the same results, and there can only be one such intermediary arrow which does that. So yeah, these two things are equivalent. And why are these two things equivalent then? Well, this just comes from reasoning about the diagram. I mean, if you look about the diagrams of R and S again, you'll see that Q of F dash RH equals PKH, which I'm defining as psi of K. So we've got a psi of K on the left. So this is just equal to this. And Q of F dash SH again from a diagram is just A of F dash PJ of H, which is just A of F dash psi J. So we have this condition here. And this is precisely the condition for the thing to be a natural transformation. Okay, so we have the remarkable result that this T here really sort of corresponds to the kind of bundled components of a natural transformation, if and only if it equalizes R and S. Now that doesn't mean it's an equalizer, I just mean that RH equals SH. Okay, so that's the critical, that this is equivalent to this naturality condition here. So that's one result we're going to need. Now the other result, okay, we've already got most of this actually. Well, the other result we're going to need, I'm calling A circle, and I'm really referring to this, which is that if there exists a unique let's have a look at our theorem again. So assume we've got this little L here from capital L to this product over objects. And now this result says that if there exists a unique R such that LR equals H, so this is a fancy way of saying that L, well, this is the kind of thing that happens when L is the real equalizer, but H is just a sort of candidate. It merely equalizes R and S. Then, there's going to exist this conversion intermediary arrow R. Anyway, this condition holds if and only if this condition holds, which is basically a similar looking condition. It's just that we're sort of saying if this works on components. So basically for any given R, I could just to argue for it, I could just say for any given R, we have that LR equals H if and only if PJ L of R equals PJH for all J. And the reason is simply that if we look at this diagram, we have that LR and H are just going to be T elements of this product. And so by just the same kind of reasoning as I was saying before, these two kind of arrows, we can think of them as tuples, we can think of each of them as tuples, and they're going to be equal precisely when they're equal in all the components. So that's how we get that one. So, okay, all that said, let's now go through the proof. So, again, we have let's restate the result again. We have that this little L is going to be an equalizer of R and S if and only if this phi with components phi I equals pi after L forms a limit of this functor A. So let's go. So let's start by assuming that we have that equalizer L and trying to argue why the capital L is an apex for a limit cone, and the pi after little l is a limit. So for the equalizer, little l, going to have to skip around a bit. So assuming this little l equalizes is an equalizer of R and S, Well, we firstly, of course, have to have that R of RL equals RS. Now, using our red star result, where is it now? I'll find it. There it is. It's our kind of workhorse for this. We have that since RL equals SL, that means that L is corresponds to a cone, okay, because it does it does commute. More precisely, what I'm saying is that we have, when we have L, if we take pk after L to equal phi k, then we will have the phi is a natural transformation from this constantly L valued functor to A, okay, because when we have this kind of condition, which basically means that these arrows raining down from this apex commute with the arrows in the base of the diagram. Okay, so that's good. So now the other thing that we need to show is that this plays nicely with other cones. So let's suppose, we've assumed that we have an equalizer. We've now shown that that corresponds to a cone with these natural transformation components, pj after L. Now we need, after little l, that is. Now what we need is that to show that this plays nicely with other cones, in the sense that if we have another cone, say this one here, psi with an apex t that also goes to A, of course, so it goes from this t valued constant functor to A, then we want to show that we have this unique intermediary arrow from one to the other. So again, since this psi here is a cone, we can use our star thing again. So since it's a cone, we have this condition, which is equivalent to saying that RH equals SH. Okay, so if we sort of bundle all of the entries in the of the natural transformation components of this kind of pretender, this psi cone here, into one arrow from its apex t to the product, so we make this h, in other words, then we have RH equals SH. But now, since we're assuming that L is an equalizer, we have that LR equals H. In fact, there exists a unique R such that LR equals H. And this is equivalent, as I said before, to saying that there exists a unique R such that PJLR equals PJH, or in other words, there exists a unique R such that for every J we have that phi j r equals psi j. And that's precisely the condition we want to sort of show that our limit cone is better than the other cone by this unique intermediary arrow r. Okay, it's just this condition pictured near the top here where this intermediary arrow is called r instead of u. Okay, so that's great. We've shown now that if we have where's the theorem, where are you? There you are. Okay, we've now shown that this condition implies this. We've shown that the right implication sign works. Okay, now we want to do the left implication sign. I mean, it's pretty much using the same logical channels, just in the opposite direction. Okay, so we'll now assume that phi is this limiting cone from so phi is a natural transformation. I mean, it's a cone, so it's natural transformation from delta L to A, and we're assuming it's the limit cone, and we're assuming it has these components phi I equals pi after L, and then we want to show that this little L here is indeed an equalizer. So I mean, the basic idea is that we can convert phi into well, I mean, firstly, let's show that this phi corresponds to an equalizing L. And we get that again from star. Instead of using a psi here, we use phi. And then we have this condition holding. So, I mean, we could rewrite this. I mean, obviously we want to replace this with where we've got phi's instead of psi's here. And then we've got pkl is psi. So these h's get replaced with l's. And we have that since this condition holds, since our presumed to exist limit phi exists according to our assumptions, we have that RL equals SL. So at least L equalizes R and S, but we still need to show that it's actually an equalizer. But we can do that because we do know, I think I've got it written down here, but we do know that given any okay, yeah, let's do it working with the equalizer. Okay, so what condition do we need for the equalizer thing? Well, we need to know that if there's another H from T to this product such that R of H equals S of H, then that means that there exists a unique R such that H is equal to LR. Okay. Now we get that because given such a H such that R of H is equal to S of H, again, we're always using this. We use this star thing here to convert this thing that where R of H is equal to S of H to a cone, this time with size, so that the conditions are correct. So we have psi k equals pkh, and it's a natural transformation. Okay, so it's a proper cone. Now we know that there exists a unique R which allows us to flip between those cones by assumption that L is a limit cone. So we have that there is a unique R from T to L such that phi j after R is equal to psi k, and sorry, phi j after R is equal to psi j, yep. For all j, of course. So we have this condition, and then our result here says this is equivalent saying there exists a unique R such for L R equals H, which is precisely the condition we need to say that this is an equalizer. So we've just shown now that this result on the bottom implies this result on the top. In other words, we've shown this left implies arrow as well.